Hi, Assalamualaikum. My name is MAMAT. Today we will present about characterization technique for various materials. For introduction, characterization technique like X-ray diffraction, Fourier transform infrared spectroscopy, and scanning electron microscopy are vital for studying materials and gaining insight into their properties. Additionally, SRT analyzes the crystal structure of material, while FTIR examines their chemical composition and molecular structure. Meanwhile, SEM visualizes the surface morphology and topography of materials. These techniques are widely used in material science, chemistry, geology, and engineering fields. SRT have identified crystal phases and major lattice parameters. FTIR provide information about functional groups and chemical bonds, and SEM generates detailed images and compositional data. By understanding the structure, composition, and behavior of materials, these techniques contribute to advancement in various scientific disciplines. For X-ray diffraction standard procedure, firstly, the sample is ground to fine powder and homogenized to minimize preferred orientation effects. Secondly, powder sample is evenly spread on a holder, ensuring smooth and uniform layer. Thirdly, SRT instrument is calibrated using standard reference material and adjusting voltage, current, and detector alignment. Fourth, X-ray beam directed at sample from different angles, measuring diffracted X-ray intensity. And lastly, the acquired data, diffraction patterns compared to known patterns to determine crystal phases. For energy depressive X-ray spectroscopy, first, prepare target sample, cut, polish, clean for analysis. Second, set up EDS instrument, calibrate, optimize for analysis. Third, securely mount sample, ensure alignment and stability for testing. Fourth, direct electron beam onto sample surface to induce X-ray emission. Fifth, collect emitted X-ray using EDS detector position nearby. Sixth, record X-ray signal while scanning sample to create a spectrum. 7. Analyze X-ray spectrum to determine elemental composition of the sample. 8. Identify elements by comparing characteristic X-ray peak with known values. 9. Quantify elemental composition, considering a factor like X-ray absorption and sample thickness. 10. Interpret result and generate a report summarizing sample elemental composition. For scanning electron microscopy, first, SEM sample was prepared by mounting it on a metal stub and coating it with conductive substance. Second, SEM calibrated for electron beam alignment, focus, and brightness by adjusting distance and voltage. Third, prepare sample placed in a vacuum sealed chamber to prevent electron scattering. Fourth, the electron beam scan the sample surface. The detector capture secondary or backscattered electron or X-ray for analysis. Fifth, photo and data analyzed using software. Image processing enhances contrast and measure particle sizes.
Assalamualaikum, my name is ARASH and I will present about the result and discussion. For X-ray diffraction for sample 22, the sample's XRD pattern displays a total of 5 peaks, indicating the presence of multiple crystal planes within the material. The red line represents the reference pattern for S22 content. The blue line represents the fluoride content and the pink line represents the scandium. A close match between the peak position and intensities of the sample's pattern and the reference pattern, it demonstrates the existence of those phases in the material. For sample 1, The pink line in the figure represents the reference pattern for calcium aluminium silicate content. Peak 4, 9 and 11 in the samples pattern align with the pink line, indicating a correlation with the calcium aluminium silicate phase. If there is a close match between the peak position and intensities, it suggests the presence of the identified phase in the sample. For energy dispersive X-ray spectroscopy, sample 22, the chemical composition corresponding to the phase present in the sample can be determined from the elemental graph. The elemental graph in figure shows the presence of neon, aluminium, silicon, chlorine, metal, zinc and neodymium in the analyzed sample. The ND particles have an atomic weight percentage of 81.3% and an atomic percentage of 69.5%. For sample 1, figure shows the presence of oxygen, silicon, potassium, calcium and zinc in the analyzed sample. The oxygen particles have an atomic weight percentage of 61% and an atomic percentage of 74.7%. Next is scanning electron microscope. For sample 22, the surface of a spring can be examined for impurities or pollutants using scanning electron microscope magnified using 120 times. Identifying the contaminants help understand their potential consequence and enables the implementation of appropriate preventative measures. Understanding the nature and effects of contaminants ensures the optimal spring performance, longevity, and resistance to corrosion and other detrimental effects. Surface features such as fractures, holes, scratch, and surface roughness can be identified and analyzed using scanning electron microscope. The information obtained from scanning electron microscope imaging aids in evaluating the suitability of the ceramic for its intended application and identifying any potential issues that may affect its performance or durability.
In conclusion, strong characterization method that offer insightful information about the characteristics of diverse materials include scanning electron microscopy, Fourier transform, infrared spectroscopy, and X-ray diffraction. Researchers can detect crystal phases, quantify lattice parameter, and analyze crystal defect and determine the crystallographic structure of materials using SRD. Meanwhile, chemical characteristics and molecular structures of various materials can be evaluated using FTIR spectroscopy by observing how materials interact with infrared light. SEM enable high resolution imaging of the topography and surface morphology of materials. It offers insightful information on elemental distribution, surface flow, particle size and shape, and surface characteristics. Overall, SRD, FTIR, and SEM play a critical roles in material characterization, allowing researchers and engineers to solve the material of various materials and unlock their potential for a variety of uses. Thank you.